Alright, we've got another synthesis video, and this is going to be a tricky one, so hopefully it'll work out for us. But we've got our starting compound here on the right. We've got a 5-member cyclopentane with this great thing outside. I can bother trying to name it. And our goal here is to create this compound on the right. So we still have our membered ring, but we've got a hydroxide attached to this carbon, a hydroxide attached to this carbon. And the big thing here is that they're on opposite sides. So there is a chirality enforcement when it comes to this compound. So pause the video, take a minute, try to see if you can solve it, and then we'll talk about our solution. Now, big thing here is that you've got chirality. These compounds have to be attached on opposite sides. This is going to be a bit of a challenge because once we have chirality, it means that we just can't, one, we don't want to operate through a carbocation, two, we want to guarantee we're going to get what we're going to get. So let's use the chirality to our advantage. What reactions can you think of where you end up producing hydroxides on the opposite sides? And the one I thought of was the epoxide. So if I use acid catalyzed ring opening of epoxides, I would have to start with this compound here. So our H3O plus will add to the OH group. We'll get attacked from the backside, and so this guarantees that they have opposite sides when it comes to the chirality. This is the best thing I could think of when I was coming up with the synthesis. Now, the nice thing about peroxides is, or epoxides, there's only one possible way to get that, and that's through a peroxide. So if we add ROOH, some peroxy acid to the alkene, we will end up getting this compound. So if you go in through epoxide, it's kind of the easy button. The question is, how do we get back to this compound? Well, it looks like an elimination reaction. And to do the elimination reaction, unfortunately, I'm going to have to do one more step. Elimination was something like a tert butoxide. If we have some type of starting compound, in principle, we could do this. Now, we could do elimination with an alcohol, or we can do an elimination with a alkyl halide. Personally, I'd rather go to the alkyl halide because those are more likely to undergo the elimination reactions. Don't get me wrong, you can have side products, but for me, it would just be a simpler step. Now, we can do it from either side, so we can draw either product. We have the chlorine here, or we can draw a chlorine here. The nice thing is there's an easy way to get from here to here, and that's if we use a half equivalent of chlorine with light. This will easily functionalize our alkane, and then we can do elimination reaction. Now you may say, well, we could do the alcohol as well. We could. The question is, how do you plan on creating the alcohol? So if this was an OH group, you would first have to functionalize it with a halogen, so you might as well go through the halogen step first. But this is how I would say you would synthesize this compound, starting with this compound. Start with your alkane, use a half equivalent of Cl2, so this way you can get the selectivity and guarantee that you only get the monosubstituted. This will put your chlorine either on this one or this one. They're both tertiary carbons, so you're likely to get both products. That said, if you use a strong base like tert butoxide, you're going to get the elimination anyway. These are the most substituted carbons in the compounds, so you're going to get that type of elimination. You end up getting the alkene. From the alkene, add the peroxo acid. This will give you the epoxide, and then if you do H+, H3O+, you'll end up breaking apart the epoxide, and this will give you the alcohols on opposite sides in terms of the chirality. So, nice little synthesis video. Hope this helped you out.